So today we're going to talk about some of the, not softer per se, but it's less deeply technical and more sort of conceptual. We'll be talking about denial of service and firewalls. Before we begin, we do have a couple of announcements. Homework 6 is due today, August 2nd, so please work on that and finish it if you haven't already. Project 2 is due tomorrow. Project 2 is due tomorrow, so I know this has been what most of you have been working on, judging by office hours. So definitely keep working on it. I know it's a lot, but you guys are almost there. And optional lab 1 is released and is due Wednesday of next week, which also happens to be finals week, which also happens to be the end of the semester. So that's not too surprising. Last time we talked about DNSSEC. So DNSSEC is how we extended the DNS protocol to ensure integrity on our results. It provides object security over our records, which basically just help us to verify that this record is correct using cryptography without having to, guarantee the integrity of our channel. We only need the integrity of the record itself. The implementation uses a hierarchical public key infrastructure. So we have a root of trust at the very top that's controlled by the root name server. And then we have a bunch of keys going back and forth. So each server will present its own public key using DNS key, and it can delegate trust to other servers using DS and RSig records, which basically provide a hash of the next server's public key. The final record ends up being signed using that same RSig record over, the A record for the IP address or something like that. And we also talked about, I guess it's out of scope for this semester, but each server is actually broken up into an upper half and a lower half, so that if you need to change your keys, you only need to re-sign it using your upper half instead of bothering the actual parent server to re-sign your keys. And then we talked about NSEC, which is how we prove that a domain doesn't exist without having to have keys online to be able to generate records. That's what we talked about last time. Today, it's going to be a lot less technical. So if you really don't like cryptography, if you really don't like DNS, we're not going to be talking. Oh, that's a lot. There's going to be a little bit of DNS, but it's not going to be related to anything that we've talked about so far. So yeah, getting into denial of service. So when we talk about denial of service, we're talking about this concept of availability. Availability is really just making sure that a service is available. It can be accessed by legitimate users. So Google is usually available to me as a service. It doesn't happen very often that I can't access Google to provide the services that I want. When we talk about denial of service, this is disrupting availability. So we're making a service unavailable for legitimate users. There are plenty of reasons why one might execute a denial of service attack. Many of these are reasons that we talked about all the way back in lecture 1, but in short, competitors might DOS each other to benefit their own services. This is highly illegal, but it's happened in the past. Criminals might DOS services, and the sort of motivation there is you receive a note one day as a website operator, pay us, $10,000, or we're going to take down your site. And for maybe shopping websites that rely on being online in order to make money, they might actually be motivated to pay this ransom. So criminals can make money this way as well. Some people will DOS services to make a political statement. So sometimes the websites of political parties or of important political figures will get DOSed. Or entities might DOS each other as part of warfare. So we've seen countries DOSing each other's services in order to gain an upper hand in warfare, basically. And there are people that will just DOS each other for fun or revenge. So this happens less often than before, but it used to be that if you beat someone in an online game, they would get mad at you and then take down your house connection for a while, depending on what sort of internet connection they had. So a lot of this does not happen as frequently as it used to, but some of these are definitely still prevalent today. So some DOS in the news. These are all, again, somewhat older articles because they were just adapted from the older version of these slides. But this article is just discussing how it's actually pretty cheap to purchase website offline time. $5 to $10 per hour and only $1,200 per month, which sounds like a lot, but considering that websites can generate millions, billions of dollars per day, this can actually be relatively cheap in the grand scope of things. Computer World talked about the rise of DDoS, which is a specific type of denial of service that we'll talk more about later. And we're seeing how criminals are increasingly targeting corporations using these DDoS attacks in order to extort money from these companies. This is also an interesting one, or one that I thought interesting in like the 20 articles that were in the original pile. But there's an attack where someone sends out a phishing email that says, hey, sorry, our website is down. Why don't you use this alternative email until we get the main servers back up? And it actually looks real because the attackers at the same time, they DOS the original website. So it actually looks like, oh, this website is actually down. So this email might be legitimate. This is the kind of thing that you might fall for if you're not looking too closely, and you might accidentally give your password out even if you are looking closely, because it's like, oh, the website's actually down. This must be a legitimate email. So these are some of the attacks that we see. Some of them are pretty clever. When we're talking about attacks, we have some main strategies that we use. So the first one is exploiting program flaws. So if you have software vulnerabilities, these could cause a service to go offline. It would be pretty trivial to write an exploit that does that. So if you have a buffer overflow vulnerability or some memory safety vulnerability, you can choose which one, you could execute shellcode that shuts down the system as a whole. So this causes the system to halt, and this service is no longer available. In web vulnerabilities, if we have a SQL injection vulnerability, you could just delete the database. And if you've deleted the database, that's pretty likely to cause your website to go down. So program flaws and vulnerabilities often lead to ways to bring a service down, to DOS the service. The other way, and this is the way that we're going to focus on a little bit more, is resource exhaustion. So anything that's connected to anything, anything that runs on a computer has a limited number of resources. If you've ever opened more than like 5 Chrome tabs, you know that your computer only has so much memory before it starts slowing down and everything starts coming to a halt. The attacker is able to abuse this by consuming all the resources themselves. So if they're consuming all the resources, say they're crunching a bunch of numbers, then no one else is able to use the CPU. And then those legitimate users can't access the service, or they can't directly access the CPU, depending on your service. So in DOS attacks that rely on exhaustion, we're going to be dealing with bottlenecks. Bottlenecks are this idea that different parts of the system, they're going to have different limits. So maybe your CPU is super powerful and your memory is super powerful, but you're still running on a really old system that uses a really old, graphics card or something. So you might have 2 parts of the system that are able to handle a lot of capacity. But if you have just this one part that your data has to flow through that is harder, that is slower than everything else, that's going to be your limit. That's going to be your bottleneck. So the attacker doesn't need to exhaust all of your system. They only need to exhaust the bottleneck of your system. Because if everything is going through that, if that gets plugged up, then nothing can flow through, even if everything else in your system is super powerful, costs $1,000. So talking about targets, and then we'll stop for questions really quickly. The 2 main targets that we'll look at are application level, so targeting the high-level application running on some system, and the network level, so targeting the network protocols that are affecting the host's internet. So the host is connected to some network out there, and we want to try to block that network as much as possible. All right, questions on any of this before we move into the first kind? I accidentally DOSed myself by running tasks on my server which maxed out the CPU, locking me out of the system for a short time. Yes, I have had that experience as well. It is not fun, but usually you can solve it by hard resetting your computer. I am shooing my dog out of my room, so if I'm out of camera, that is why. All right. All right, then let's move on to application level DOS. So in this, we're targeting the resources that the application itself uses. This might also exploit features of the application itself. And some of these attacks are going to rely on asymmetry. asymmetry is a really powerful tool for DOS attacks because it means that a small amount of input will generally result in a large amount of resources consumed. So if I can send like a tiny piece of data and that data causes like a really long computation, for example, that's going to be asymmetrical because it's just a little bit of input versus a large amount of output. There's no, this is definitely favoring the attacker. So for resource consumption, when we try to force the server to consume all of its resources, we generally have a lot of opportunities available to us. If we're thinking about how might we write code to run on the server to consume all of its resources, we have a lot of options available to us. So I've just written a little bit of DOS code here. Most of these would be defended against in the real world, but you can start to get an idea of what these do. So here what we're doing is we're writing to this file. So we're writing to this temp junk file. I realize that none of this is actual like valid CA now that I think about it. We have a buffer, which is not terminated by a semicolon for some reason. And then we're just writing to the same file over and over and over and over again. And this will just eat all of the file system space. We're writing data to the disk as fast as possible. So now no one else is able to use the disk because we've consumed all of the data. All right. So that's how we consume the file system. What if we want to consume the RAM? Well, here what we can do is while in this infinite loop, we'll just say malloc and then a bunch of data. I believe this is 1 GB. And it doesn't matter that we have a memory leak here. The point of our program is to consume as much memory as possible. So here we're just consuming all the RAM and making sure that no other program gets to use it. All right, so we've done the disk, we've done the RAM. How about the CPU? Well, if we run this code, there's this fork function here. And what the fork function does is it actually creates a duplicate of the process. So it'll actually take the currently running process, duplicate it. So now we have 2 instances of the running process. And now both of these processes go back into the loop. They'll duplicate again into 4, go again, duplicate into 8. And basically this will spawn a zillion processes, and suddenly all of these dummy processes are running. The real processes don't have any time on your computer to run because all of these processes are taking up all of the threads on your computer. And finally, maybe we don't want to exhaust the space on the file system, but instead we just want the disk to do a lot of work and have to like write a million tiny files. So what we're going to do here is in this infinite loop again, we're going to choose a random file, open it, write just some random data to it, close it, and then do that over and over and over again. So we're opening a bunch of files, running a tiny piece of data, closing it, opening another one, doing this a million times. And what this is going to do is it's forcing the disk to write a bunch of tiny files all over the disk. And it means that no other process has the opportunity to write their tiny little files because they're busy writing all of our tiny little files. So you don't have to memorize any of this code, but the key here is we can force a server to consume all of its resources pretty easily. All right. Sometimes we're not going to, brute force through and write, infinite looping code. Instead, we'll take a smarter attack. So algorithmic complexity. Technically 61B is a prerequisite for this class. We've talked about different data structures before. So let's say that we are writing some application out there and we need to sort something. That's a pretty reasonable assumption. I sort things pretty often in my own code. What if the attacker intentionally chooses inputs to cause the worst case runtime to occur? I'm starting to think that some of this is appearing out of order because this is not how I originally wrote these slides. But the key to algorithmic complexity attacks is that even though some data structures, they'll run in n log n time on average. So, quicksort and merge sort, they both run in n log n time, but they have different worst case running times. So I'll skip ahead a little bit here. Looking at quicksort, which is, the one that you'll probably use if you call a standard library function, quicksort actually has a worst case running time of O of n squared. Don't worry too much if you're not familiar with the specifics of how this big O notation works, but the key is that both of these have the same expected runtime. But quicksort, if you give it some malicious input, will take a lot longer. For quicksort, the exact input would be basically the same number 10 million times. So what quicksort will do is, even though in expectation with normal data, it will sort in n log n, the worst case runtime will cause it to do n squared, and that will take a really long time, versus a safer choice like merge sort, which will always be n log n even in the worst case. Even if you give it, the same number 1,000 times, it will still do n log n and not O of n squared. So the sort of takeaway here is, if you're ever writing code that is going to be run on data that's not trusted, and this code has, a limited amount of resources, you should probably choose some algorithm or data structure that has a good worst case runtime, because the adversary might try to invoke that worst case runtime. So in this case, it would be merge sort or quicksort, but it really depends on your application. Okay, so those are just two examples. You can, of course, get a lot more creative with how you choose to DOS things, but these are just two examples of strategies you might see. You can also run the sort in a task which is terminated after a certain time. Yes, we have other, we'll get into defenses on the next slide, but yes, it's a very good observation. Ardelin asks, can't we just shuffle? I'm not quite sure what you're trying to say there. For any sorting algorithm, if you input the same number 1,000 times and you shuffle that, that's still going to be the same number 1,000 times. And then when you try to sort that using quicksort, that's going to take O of n squared instead of O of n log n, regardless of whether you shuffle. So maybe you're describing something else that I'm not quite seeing, but yeah. All right, so getting into some of the defenses, the first thing that we need for application level DOS is identification. You need to be able to know which request comes from which user, because if all you see are a bunch of requests, you're never going to know if either I'm getting one request from the same person 10,000 times, or I'm getting requests from different people, and it's just, my service is really popular today. So you have to be able to distinguish which requests are coming from which users. You also, this is going to require some method of identification and authentication. Maybe they need to enter their password or something. And sort of the thing to keep in mind is that if your authentication method is itself expensive, it might also be vulnerable to DOS. But step 0 is be able to identify traffic and be able to identify which user it comes from. Ardelin, I see you unmuted yourself. Did you have something you wanted to ask? Okay, you just muted yourself, so I'll take that as a no. Once we can identify different traffic, we need isolation. So ensuring that one user's actions don't affect another user's experience. This is kind of the general ideal that we want. We want to make sure that even if one user is running a million threads, they're not going to affect any other user's experience. So in general, you want to enforce isolation, and it's really going to depend on the specific code that you're writing, how you choose to implement this. You can also implement something called quotas. So ensuring that users only have a certain proportion of resources, That's not grammatically correct. Some examples here are maybe you only allow trusted users to execute expensive requests. So you assign everyone a quota of 0, and you say only certain users have a quota of maybe 2 expensive requests per minute or something like that. You could also say, oh, each user only gets 4 gigabytes of RAM and 2 cores of the CPU and nothing more. So this means that if you have, a 32 core CPU, you can have up to 16 users and they're all completely isolated from each other. What Friedrich brought up earlier about making sure that the task terminates in a certain amount of time is also related to this. We say that your process can only execute for 10 seconds and no more. If you want to execute for like 30 seconds, you have to contact the system administrator and they might make a special exception, but that would probably fall under quotas. Couldn't the attacker just pretend to be a bunch of different users? Yes, that is very good observation. What you've described there is something called a Sybil attack, which is based on some story, but basically, how do you differentiate a bunch of malicious users controlled by one person versus a bunch of actually malicious users? This just falls under the identification of the slide, and we're not going to get into how to actually do that identification. But in those cases where you're allowing the attacker to create a bunch of users, there are a couple of alternatives that I'll propose in the next slide that might work out a little bit better, but very good observation. So another one is proof of work. We talked about proof of work in Bitcoin, which is basically you force someone to perform a certain amount of computation to ensure that they've done a thing. And we can apply the same technique to DOS mitigation. So if we're forcing users to spend resources to issue a request, what we do is now if the attacker wants to consume, let's say 100 cycles of CPU, now the attacker also has to compute that same number of CPU. So now we're forcing the attacker's attack to scale with how much they're attacking us. So we basically make it more expensive for them, and we assume that that will reduce the frequency or the intensity of attacks. Another example of this is to add a CAPTCHA. So we talked about CAPTCHAs at the end of the web unit, and a CAPTCHA is basically you have to solve a quick puzzle using a human that only a human can solve. And the idea here is now the attacker has to either pay money to solve all of these CAPTCHAs using a CAPTCHA solving service, or they have to go through and solve like literally 100 CAPTCHAs. So the general idea is force users to spend resources, and that means that the attacker will now have to spend their own resources to execute a DOS. And the final and probably the simplest approach we can take is over-provisioning. So instead of trying to defend against DOS attacks, what we'll do is, all right, instead, I'm just going to purchase, 100 computers, let them all run in, some clustered mode or something. I don't know. And the idea is we're spending a lot of money to allocate a lot of resources so that even if we do get DOSed, it's only going to affect, a small proportion of our total resources. And the idea here is kind of similar. We force the attacker to spend more money to actually be able to deny service to other people. But of course, the drawback is this can cost a lot of money. As we all know, money is hard to come by from time to time. And it'll really depend on your threat model whether this is actually a valid defense or not. If you're up against something like the NSA, they have a lot of resources and even over provisioning might not be enough. But for most attackers, this is often going to be the most effective defense. This is where you consider security as economics. You really just need to make it expensive enough that they're going to DOS someone else instead of you. So if you're willing to pay money, they're probably not going to be willing to pay that money and they'll go elsewhere. So it's really embodying the idea of paying for more expensive security is more expensive. There's this idea of a content delivery network. So instead of you purchasing a bunch of resources, there are services out there that will actually just purchase those services for you. A big one is Cloudflare. And the way they work is they basically sit in front of your internet traffic, and they'll almost be like a cache for your website. So they'll fetch your website from time to time, and then they will handle all of the requests. And they have a ton of resources. So everyone is paying for Cloudflare. And so Cloudflare is able to allocate a lot of resources to defend against DOS attacks. And basically everyone is pooling their money together in order to purchase these services. The downside to this is that occasionally Cloudflare will completely go down and bring the entire internet down with them. This happened, I believe, earlier this year or last year. I actually don't remember, but there are pros and cons to this. But that actually wraps up application level DOS. Are there any questions on, I guess, resource exhaustion and these defenses? All right. If not, we'll move on to network level DOS. So this is probably what most people are thinking of when they're thinking of DOS. This is the DOS that a child would do if they're mad at someone that just beat them in a game and tried to take them down online. So on a network level DOS, we're approaches. I'm pretty sure that's supposed to be attacks. I'm not sure. Oh, the approaches target network protocols to affect the internet access of the victim. Sorry, I couldn't tell how I wrote the sentence for a moment. One simple example is sending a large number of packets to the victim. The approaches we'll take here are either overwhelming the victim's bandwidth. So if I can upload, say, 10 megabits per second, and the attacker sends me 20 megabits per second, suddenly my bandwidth is completely saturated. Nothing else can get in or out of my network. Here, we're going to send a lot of maximum sized packets, and we'll contrast this with another attack shortly. The other idea, which is a bit less intuitive, is to overwhelm the victim's packet processing capacity. So maybe I can send 100 megabits per second, but maybe my router is only smart enough to handle 10 packets per second. If the attacker sends me 20 packets per second, then I'm going to end up with more packets than I can process per second. And then when I'm trying to send my own packets out, it's like, oh, sorry, I can't process this many packets. And here we're actually going to send a lot of minimum sized packets. So we're not consuming much bandwidth. Instead, we're consuming the packet processing capacity itself. All right, so those are the basic attacks. And we can definitely scale this up very, very large, very quickly. So distributed denial of service, which is DDoS, a term that many people will have heard on the internet. The basic idea is just to use multiple systems to overwhelm the target system. So if we control, instead of one system, let's say in this diagram, we control, what is that, 6, then we can instruct all of these computers to send data to the victim all at once. This also makes it hard to filter out DDoS traffic, because now instead of all the traffic coming from one person and you can just try to filter that out, now you've got data coming from every direction and you don't know what is real and what isn't. So DDoS is definitely one of the more destructive DOS attacks out there, and it can be made really efficiently through something called botnets. So a botnet is a collection of compromised computers controlled by one attacker. So let's say they wrote a piece of malware and this malware spread through the internet. And this malware, all it does is it waits for commands from the attacker's computer. Once it receives this command, it will start sending a bunch of data to a single computer. So now what the attacker can do is send a command saying, send a lot of data to this one victim. And now this one victim is receiving data from every computer in this botnet, and its connection is probably going to be overwhelmed. All right, that's DDoS. That's sort of what most of us have heard of before. There's also something called amplified denial of service. So in amplified denial of service, which I've just realized is relatively hard to say and is not abbreviated as DDoS, so give me a moment. I will fix this right now. Amplified denial of service, which does not have a acronym yet. The idea is to use some sort of amplifier. So an amplifier is something that if I send a small request to it, I'll get a really large response back. So the analogy that I saw online is, hello, I'm calling some pizza place. I would like to order one of everything. Do you think you could call me back and let me know exactly what I ordered? And hello, my name is Perrin, and this is my phone number. So now I'm going to hang up. The pizza company is going to call Perrin and say, hello, you ordered, a pepperoni pizza, a cheese pizza, a pizza with pineapple on it, and a million other pizzas. And now Perrin's getting a lot more data than he asked for just because I made this small phone call. And we can do the same. And we can use the same idea in the real world. So, the first thing we need is to spoof our source address. So we say, hello, my name is victim, and I would like, this really large response. And an example that we've seen, and this is where DNS is going to come up very briefly, is in DNS. So in DNS, we send these requests, and they only contain a tiny amount of information because they just contain the question. But when we get the response, we got back 20 different records, with DNSSEC, they're even signed. So we've got a lot of cryptographic data as well, and we get authority data, and we get additional data as well to help us with our request. So we sent a small question and we got back a really large response. If we say, hello, my name is Perrin, and I would like the address of google.com with all of the DNSSEC information, please, then Perrin's going to get a really large DNS response. So some benefits to this, well, benefits if you're the attacker, are that the attacker's identity is now concealed because the packets aren't coming from the attacker. They look like they're coming from the amplification server, the DNS server, or whatever server you're using. This also means that if the attacker has a small amount of bandwidth, they can amplify this small amount of bandwidth to overwhelm a larger attacker. So if I only have, say, 1 megabit per second, my victim has 10 megabits per second, and my amplification server will amplify my output by 20 times, let's say. Suddenly I can send the equivalent of a 20 megabit per second attack to my victim, and then they'll be overwhelmed, even though I only have 1 megabit per second, because this amplification is just so great. These amplification servers are often going to have massive bandwidths because they have to serve millions of users. If you imagine the popular DNS servers, they need to serve literally people asking around the world, hey, what's the address of XYZ? So the bandwidths of the amplification servers themselves are usually not a problem. Of course, there are drawbacks, again, if you're the attacker. You do need the capability to blind spoof. So you can't do this with TCP, since in TCP you need to be able to respond to that SYNAC, and you can't do that blind. So usually these protocols are going to go over UDP. All right, that is how we DOS people on the internet. Let's talk about how we defend against these. So the main thing that we'll talk about is something called a packet filter, which is also going to come up a lot very shortly in the firewall section. But the general idea is, all right, we're receiving a bunch of packets that are coming from the attacker, and they're overwhelming our bandwidth. So let's just discard any packet that's part of a DOS attack. Okay, sounds easy in theory, but how do we actually do that? Well, let's say we know the attacker's IP address. Let's just discard any packets that are coming from that source IP. Maybe if I'm receiving a bunch of packets that are all coming from 1.2.3.4, and they're all like large and they're all meaningless, we know, okay, maybe this is a DOS attack. We'll just block all packets from 1.2.3.4. Just you have to keep in mind that the packet filter has to be before the bottleneck. So it doesn't help us if the packet filter is after the bottleneck, because by that point, the bottleneck is already overwhelmed, and blocking packets after the bottleneck isn't really going to help us out. Okay, how do we get around this? Well, most of these packet filters are going to rely on the fact that packets are all coming from the same IP address. So we could just not do that. If we spoof our packets still like they're coming from somewhere else, then the packet filters can't filter by IP address anymore. And this actually becomes kind of hard to defend against. What we usually rely upon here is we're saying to the internet service providers, hey, please make sure that you're not allowing people to send packets that look like they're coming from somewhere that they're not, because then we're not going to be able to discern the identity of the source. Of course, we talked about earlier, in a DDoS attack, we're actually sending packets from a bunch of different sources. So we're not spoofing anything anymore. We're actually just sending a bunch of packets from a bunch of different sources. So this is even harder to defend against, and we need a lot more sophistication in our packet filters to defend against DDoS attacks. And we won't go into the techniques that they use because they're really quite complicated. All right, and of course, we can, again, just over provision. So this was fairly effective last time. It'll be fairly effective this time. Just purchase enough bandwidth and purchase enough equipment to make it hard for attackers to overwhelm just the sheer amount of capacity that you have. So again, depending on your threat model, this might end up being the easiest defense that you can take. All right, so that was network level DOS. Are there any questions on this? All right, we're going to talk about a specific example of of a DOS attack that looks like it's network-based, but it's really application-based. So in an attack called SYN flooding, we're going to exploit the creation of many TCP connections. So if you think about it, each TCP connection needs to have some sort of state associated with it. We need to store the sequence numbers that the client is using. We need to store the ACK numbers that we're going to be using. We need to, when we receive the data, we need somewhere to store that data. So this TCP connection takes up memory in our system. If we can establish like 1 million connections with the server, we're going to cause the server to consume a lot of memory because it needs a bit of state for each one of those connections. And it's actually worse than that. We don't need to actually establish those connections. All we need to do is send the first SYN packet. So if you remember, the three-way handshake is made up of 3 packets: the SYN from the client, the SYN ACK from the server, and the ACK from the attacker, or from the client. We only need to send the SYN, because the moment we send the SYN, the server goes, oh, someone's trying to make a connection with me. I'll just allocate some state for this connection so that I can keep track of it in the future. Well, if the attacker just sends a bunch of SYN packets, the server is going to think, oh, 5,000 computers want to make a connection with me at the same time. So now we're causing the server to expend a lot of resources without even having to do anything ourselves. So how do we defend against this? Seems like a pretty reasonable attack. There must be some good defenses that are out there. Well, we could over-provision. So maybe we just make sure that the server has a lot of memory. This could be expensive, same as before. We could also say, make sure that only legitimate connections are going to create some sort of state. If we receive a bunch of packets that are coming from the attacker, don't allocate state there. Well, this sort of runs into the same problem as standard packet filtering for network level DOS attacks. It's even harder for us because in this case, it's hard to distinguish legitimate traffic. When you first receive a SYN packet, that's all you get. You can't know anything in that moment. Is this actually going to be a valid connection? Or is this going to be, a SYN flooding attack? So it's hard to distinguish traffic so early on in the connection to know whether it's good or evil. The attacker also has the ability to spoof the source address, since they only need to send the SYN. They never need to finish establishing the handshake here. So we've gotten ourselves in a bit of a bind. We can't distinguish traffic so early on because this is literally just a SYN packet, and the attacker can do this off path. So the attacker is able to use any source of address they want because they don't really care about the SYN ACK that we're sending. Well, there are a couple of other network-based ways that we could solve this, but the way that we're actually going to solve this that we'll discuss today is something called SYN cookies. And the solution is just don't store state. And when I first saw this, I was like, how on earth would you do that? You need to save your sequence number, for example, somewhere. And the key here is actually really clever. We're going to, instead of storing the state ourselves, give the state back to the client. Interesting. Well, we can say, okay, client, thank you for wanting to establish a connection with me. I'm going to create the state, but I'm just going to give it back to you. And just make sure you send it back to me next time you contact me. And the way this would work in some magical ideal world is we've got the client, we've got the server. The client says, hello, I would like to form a connection, sends the SYN packet. The server, it generates state, it has to remember some state for this connection, but it doesn't save it. Instead, what it's going to do is it's going to encode that state with some secret. So it might encrypt it using a secret key and then MAC it just for good measure. And it's going to send it back to the client. So it sends the SYN ACK and it says, here's the state for the server, take good care of it, send it back to me when you are ready to make your next request. And this is clever because now the server doesn't have to store anything. The client is the one who has to store the state. And then when they respond with the ACK, they'll say, okay, server, here is your original state that you were working with earlier, and here's my data, and here's the rest of the connection. That's pretty clever. Now we don't have to store any state because the client's going to store it for us. But TCP, Yeah, the handshake's complete. So now that the handshake is complete, we do have to store the data coming from the client. So now we'll store this state directly, but only after we've completed the handshake. This is clever, but TCP doesn't have any mechanism for this. TCP doesn't have some magic state field where the server can put its own state. We've already, established TCP, and this is happening afterwards. So we don't have a way of solving this. Does anyone have any idea where could we possibly store the state for the server? If we need some sort of value that is chosen by the server, and the value doesn't have much meaning on its own, it just has to be some random value initially. What's a value chosen by the server that is random and is part of this handshake? We're looking at what value in this three-way handshake does the server get to choose? All right. In the interest of time, I'll just give it to you. Yeah, the sequence number, exactly. So we'll say, okay, the client sends this in again. The server doesn't generate the state, doesn't save it. They're going to encode it in the sequence number itself. So, they didn't get to choose X, but they can choose this Y. So instead of choosing a completely random Y, we're going to put it to good use. We're going to say, okay, this sequence number is actually going to be some encoded state, and maybe it can includes a MAC as part of it. And we know the client's going to remember the sequence number because you have to as part of TCP. And then in the ACK, they'll send back the sequence number or +1, which is the encoded state. So now the server can just subtract 1, get back its original state. And only now does it go, okay, I'll save the state and allocate it in my own memory. So yeah, the first time I saw this, I was like, this is really clever. We're putting the state somewhere where, maybe it wasn't meant to go, but the sequence number is just completely random. So we can put our state in that sequence number and the client will just send it right back to us. So now we're passing this state off to the client. And I think it's really clever. I think this is a really cool defense. The observation here is that because the server doesn't create state until the handshake is completed, the attacker has to complete the handshakes. This means that filtering becomes easier when you implement SYN cookies. I don't think I mentioned the name. The name of this defense is SYN cookies. But because now the attacker has to complete all of the handshakes in order to execute the DOS attack, now we can more easily filter out the traffic coming from the attacker because all of it will be coming from the same source address because it all has to go back to the attacker if they want to execute this attack. We can generalize this idea to more than just TCP. In general, if we want to defend against attacks that rely on the attacker causing the server to allocate a bunch of state, we just say instead, okay, this state, I'm just going to give it to the client. They'll hold on to it for me. And then when they get back to me next, they'll give me back the state. I'll say, okay, tweak my state a little bit, re-encrypt it and remac it, give it back to the client. And then next time they'll send it back to me again and so on and so forth. This is basically the core idea of how we mitigate some attacks. We don't store state ourselves. We just encode it, give it to the client, they'll give it back to us. And again, I think this is really clever. Of course, you need enough bits to be able to encode the state. So if your state is several gigabytes, maybe this isn't as feasible. We also have to make sure that when we check the state, we're giving the state to the client, so we have to make sure they don't tamper with it. We have to make sure that it's relatively inexpensive for us to actually verify the state. Otherwise, this becomes a DOS vector in itself because they'll just send a million pieces of state to us and we have to verify all of it, and then that becomes slow. Does this general idea make sense? Any questions on how this works? All right, well, that is it for DOS. We'll get into firewalls next, but why don't we take a break until 4:30 because my voice is tired and my brain's a little bit tired today. So we'll take a break and then we should be able to make it through firewalls before the end of lecture. So we'll be back at 4:30. All right, so that was DOS attacks. We've talked a little bit about how we both execute and defend against DOS attacks. Now we're going to dig into something we touched on briefly, but we wanted to cover in a little bit more depth, firewalls. So let's talk about the motivation for firewalls first of all. Let's say you are a system administrator. You've just been hired at, I don't know, Google to be their chief of security, and you need to defend their systems. How do you protect your systems against external attacks? Well, if you work at Google, there are many servers and there are many employees and they have many computers. First thing to notice is you work at Google, your computers are doing a lot of things, and the more network services you have, generally there tends to be more risk. So if your computer makes a bunch of different connections and maybe it has like 5 servers running, it gives attackers more opportunity. So it gives them a greater attack surface, would be the technical term that we're using here. You could turn off all the network services, but this is often infeasible. Sometimes you need services running in order to be able to print things. Sometimes you need services in order to be able to remotely log in. So, we've all SSH'd into a server at some point. And the other observation is not only are your computers doing a lot of things, but you have a lot of computers. Google has like millions and millions of computers, and we want, well, not want to, we're being paid to secure all of them. And all of these systems are different. So some servers are running Windows, some are running Linux, some are being run by users who know what they're doing, and some are being run by users who are really confused and don't know much about security. So how do you defend against this, really diverse landscape of computers? And maybe there are even some systems that we don't even know are there. Maybe someone installed a, I don't know, Alexa in the middle of Google, and now that system is there communicating with the network. So how do we deal with all of this? Well, I think at this point, it's probably somewhat infeasible for us to secure individual machines perfectly. So we're going to secure the entire network. We're going to install a single machine that's going to filter out all of our traffic for us so that we don't need to put too much work into making sure every individual machine is secure. So here's where we're talking about firewalls. This is a general diagram of what we'll be talking about very shortly. But the idea is to add a single point of access into your network and out of your network. This point of access is going to be a reference monitor. So think all the way back to ensure complete mediation, again from lecture 1. And any traffic that could affect your vulnerable systems, the idea is it has to pass through this firewall. All right, how do we define what this firewall does? Well, we say it's controlled by some sort of security policy or just a policy. We say, okay, what traffic is allowed to exit the network? So we have a bunch of secure computers here. What are they allowed to connect to in the outside world? We also have to say what data from the outside world is allowed to enter our network. So sometimes we want to connect to the outside world. Sometimes the outside world wants to connect to us, and we have to define exactly what is allowed and what isn't. This is called our inbound policy. And what's going out of the network is our outbound policy. This model is based on a relatively common threat model. We assume that users inside the network are trusted and those outside the network are evil. So we've got a bunch of attackers outside the network that are trying to get in. That's why we call it, a wall, and it's a firewall. So this model is based on relatively reasonable assumptions. Let's think about this for a moment. What is the policy of a standard home network? Let's talk about outbound policy first. What traffic are you usually allowed to connect to on the internet? Is your home network usually blocking, all internet websites? Or does it usually allow all traffic through? All right, maybe people aren't too sure about policy, so I'll get into it. So usually, I'm on my computer. My computer's making connections to Google. It's making connections to Zoom right now. It's making connections to Slack because I've got that open in the next window. So our outbound policy is to allow all outbound traffic. Just allow it. If we're inside the network, we just say you can connect to anything outside of the network. All right, what about inbound policy? Only some traffic is able to enter the network. So what traffic should we allow through? Well, we know that if I want to send something to Google, Google has to send something back to me because they have to send me a response. So I'm going to say allow inbound traffic that's in response to an outbound connection. It's a little bit wordy, but I think I kind of understand what's going on. If I send an HTTP request, I should see some response a short time later that gives me the data in return. So I'll allow that traffic, and I'll allow traffic to certain trusted services. So maybe I have an SSH server running on my computer and I want to allow access to that. But other than that, deny all other outbound traffic and inbound traffic, sorry. Deny inbound traffic because we don't want random people on the internet connecting to my computers at home. So this is what you'll see on most home networks. Of course, it can be a little bit more complicated than this. And there's this thing called NAT, which we won't talk about. But this is sort of a general idea of what you might see in a typical setting. So the diagram here, we are saying allow all outbound traffic. So all traffic going this way is allowed to get in or allowed to get out. All traffic going this way, well, we are looking at that a little bit more carefully. We say there's some trusted traffic that we allow, but all others we're going to deny it. It's not allowed through. Okay, what did we do here? We set this default to default deny, but we set this default to default allow. How do we choose between these two policies? Well, we have to handle all traffic in one of two ways. We have to either allow it through or not allow it through. There's not really much of a choice in between. So what do we do with traffic that isn't explicitly, allowed or denied? Well, there are two main policies that we just covered earlier. We could say default allow. So allow all traffic, but deny a specific subset of traffic on our deny list. So as problems arise, maybe, that computer got hacked because it's vulnerable to the internet. We're just going to say deny traffic to that specific computer. So as problems arise, we add them just to the deny list. Alternatively, we could do default deny. So deny all traffic, but allow those on a specified allow list. So as needs arise, or as users complain that, oh, I can't access, Google, add them to the allow list. Why did I put a question mark there? I'm not sure, but that's not supposed to be there. Which of these is best? Well, on one hand, default allow is more flexible, we'll get less complaints, but if you have a flaw in that list, that flaw is a vulnerability and that can be catastrophic. On the other hand, default deny, it's a little more conservative, you might have to fiddle with things a little bit more, but the flaws aren't as catastrophic and they're generally easier to fix. So takeaway, you generally want to go with default deny. That's generally the best default policy. And again, we're thinking back to security principles this entire course. Here, let's think about consider fail-safe defaults. Default deny would definitely be fail-safe because if there's a failure, we want it to default, block all traffic instead of exposing us to the entire internet. All right, how do we actually implement these firewalls? Well, there are a couple of things that we can do. The first one we'll talk about is something called a packet filter. These are going to inspect the content of our network packets, and we just choose what to do with them. We're not allowed to look at the history of the packets that we received. We have to make our decision. Oh, sorry. Option one, option two. So for all packet filter, option one is to allow the packet through the firewall. So we forward it onwards. We say, go on. Or option two is deny the packet from passing through. We drop it. Dropping is just, deleting the packet and causing it to never be sent again. The technical term here is dropping it, probably because it has to do with some metaphor of carrying packets around. But in a stateless packet filter, we only get to look at the packet itself. We don't have any sense of history. So we have to make all our decisions based on just this one packet. This is relatively simple, but it has some trouble implementing more complex policies because more complex policies are generally going to require some history. So let's think about the home network policy from earlier. Allow outbound traffic, allow inbound traffic in response to an outbound connection, and deny all other inbound traffic. What's the issue that we see here? If we don't have access to history, which one of these bullet points would be difficult to implement? 1, 2, or 3? Assuming we have no access to history. Yeah, 2. You have no idea if a packet is coming in response to an outbound connection or not, because you have no idea what the connections are, because I have no memory. This is completely stateless. So we can kind of do this. In TCP, you can implement this with a bit of a hack. So what we'll say is allow inbound traffic with the ACK flag set, and deny inbound traffic without the ACK flag set. Because remember, to form a connection, you need to send a SYN packet that doesn't have the ACK flag set. But all other traffic, we're assuming for established connections, is going to have the ACK flag set. Wow, say that 5 times fast. The sort of idea we're relying upon here is if some malicious attacker sends an ACK packet to us that was, completely in response to nothing, it was just sent without having asked for it, the internal computer will see that and say, I'm not supposed to get that. I'll send a reset packet just to be safe. So we can kind of implement this. It's a bit of a hack, but it almost barely works. For UDP, it's impossible. UDP has no concept of a connection. It just literally sends the packets as they are. And so any sense of a connection is usually implemented at the application layer, and we have no hope against them. So stateless packet filters, not great. Well, the alternative that we are working with is stateful packet filters. So now we have the idea of state. Now we can keep track of inbound and outbound connections, and we can see, we established a connection because I saw a SYN, and then I saw a SYN-ACK, and then I saw an ACK. So now I have this idea of connections because I can remember history. The thing to notice is that all connections have packets going in both directions. I form one outbound connection to Google to ask for a web page, but Google is still going to send me packets as part of that outbound connection because it needs to send me a response. So all connections have packets going both ways, which is why stateless filters have trouble with the idea of connections. Now that we have the idea of connections, we can define what connections are allowed or denied. And ultimately, this filter is still just dropping packets or forwarding them onwards, but now it can have an idea of, this packet is associated with this connection, drop it, or this packet is associated with this connection, forward it on. So some rules that you'll see, and I'll just use some fancy syntax here because it's good to get you exposed to it, I suppose. Maybe we'll allow all traffic from all ports on 4.5.5.4 to this destination here, 3.1.1.2, but only on port 80. And we're saying only TCP is allowed. So we block all other protocols, we block all other sources and destinations, except for this one special case. All right. And, again, keep in mind that this one connection will have packets going both ways, which is why a stateless filter would sort of struggle with this. I might also say, allow all internal networks, so this /int stands for internal networks, allow all connections that are on port 80 and as long as they're TCP. So this says allow all connections with destination port 80 to the external world. And port 80 is the default port for the internet. So this really, or for the web. So this really says allow all outbound web connections. And we can also say allow all internal connections to external connections, or internal hosts to external hosts. So this says just allow all outbound connections. This is what you'd see on a typical home network. Or maybe you want to be a bit more restrictive, or actually let's go in the other way. We're allowing inbound connections, so all connections from the external network to this one specified host. So we're allowing only inbound connections to this one host, presumably on our internal network, and only to port 80. So we have a lot more flexibility with these rules, and we don't have to just stick with, TCP, UDP, IP, and nothing else. Stateful packet filters can also keep track of the state of applications themselves. So maybe our stateful packet filter will not only track, this is a TCP connection to port 80, but it will also keep track of HTTP requests and responses, and we can write rules based on that. FTP is another common protocol used for transferring files. File transfer protocol, makes sense. And maybe our stateful packet filter will keep track of what files are being sent because it can reconstruct that connection. So let's just, what time is it? Really quickly, let's talk about what state do we need to keep track of an FTP connection. Let's say allow all FTP connections inbound except for those logging in as root. Well, in a stateful packet filter, we're allowed to keep state. What kind of state do we want to keep? We know we need probably the source and destination, IPs and ports. That's relatively straightforward. We also need to keep track of FTP data. So whether this is an FTP connection, that needs to be some Boolean in our state. Maybe we also need the status of the FTP connection. So we need to know, oh, right now the user is executing, a password command. And we want to keep track of the username because this is really what we care about, except those logging in as root. We need to make sure the username is not root. We can be a bit more careful with this. We really just need the first 5 bytes of the username because what we want to see is root, 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 null. If we keep track of the entire username, then the attacker could send like a 2 GB username, and then you end up DOSing the firewall because the firewall runs out of memory. So, the takeaway here is to keep track of applications, firewalls generally need to be smart about how they store state, and they need to be really smart if they want to avoid DOS attacks. So it's kind of subtle, but I wanted to throw that in there. So we're talking about packet filters. We have a lot of ways to subvert them. Let's talk about another simple example. Deny all connections that contain the string root at all. We're going to say that we deny packets that contain any sequence of the bytes R, O, O, and T. So if at any point we see, oh, there's an R, an O, an O, and a T in this packet, then we'll just say, nope, this packet's not allowed through. Otherwise, sorry, screen broke. I was sharing the right thing. Sorry, it took me a moment. Otherwise, we say, allow all other packets. This seems like it should be pretty easy in theory, but it starts to run into problems. So let's talk about some examples where it does work. We see A to B, hello world, that's fine. We see C to D, this is login packets. So maybe we should be careful about this one, but we'll let it through. And we see, oh, continuing from the earlier connection, sequence number 8 as root. And we see, nope, that's not okay. Don't want the string root anywhere in our packets. So we deny that. But we can be a little bit finicky with this. Let's say we have our firewall coming in and we have a bunch of packets. These packets are all sent by the attacker. So the attacker gets to choose what sequence number they come in. And the first thing that you'll notice is maybe they've broken this packet up. So now none of these packets contain the string ROOT because the attacker has intentionally broken this packet up. One packet contains R, one contains O, one contains O, and one contains T. And all of these will individually be let through. Additionally, packets can arrive out of order. So maybe the attacker chooses to send this O first, then chooses to send this T, then maybe this R, then this O. That's not even going to look like root. It's just going to look like a bunch of letters being sent. So we need to be a little bit smarter about how our firewall reconstructs this TCP connection. All right, I've sort of also delivered this slide out of order, so sorry for the confusion, but the basic idea is the attacker can split the packets and they can reorder the packets to try to confuse this stateful packet filter. But the adversary can be even more finicky. So I know this diagram is really complicated, but just bear with me for a moment. So IP packets have this idea of a time to live, which is really just how many hops is a packet allowed to take before the packet is dropped. And this is really just to avoid, infinite loops. The packet will just keep decrementing its time to live until it disappears. This way you don't get packets that are sent back excuse me, back and forth for the rest of eternity. The attacker is given the pretty easy ability of telling how many hops away a server is. What you do is you keep sending ping packets, which is a packet that will be sent back to you if the server receives it. And you say, okay, time to live 1, send that, didn't get a response. Time to live 2, send that, didn't get a response, probably died along the way. Time to live, 5, eventually you get there. Oh, I got a response. The server must be 5 hops away. So it's pretty easy to tell how many hops away a given server is. And now what the attacker can do is start sending a bunch of different packets. And these all have, and they have the same sequence numbers, but different times to live. So let's just look at these first 2 examples here. The attacker wants to get the letter R through. So what they're going to do is send 2 packets, N and R. They have the same sequence number, so it looks like these both belong to the same connection. But N has a time to live of 16, so maybe it dies right here. And R has a time to live of 22, so it will make it all the way to the destination. And they can do this with the rest of them, so they send an O and the I, but only the O will actually make it. They send an O and a C, but only the O will actually make it. And they send an E and a T, and only the T will actually make it. This is really confusing for the firewall, because what the firewall sees is, I'm getting a bunch of these packets, and they all look like they belong to the connection, and I'm not sure how to handle this. Because the firewall doesn't know which packets are going to be dropped. The firewall doesn't know which packets are going to be received. So the times to live generally vary anyway, since remember on IP, the packet's allowed to take different routes as it sees fit. So you could generally have varying TTLs anyway, so you can't just rely on the fact that you're going to use the highest or the lowest TTL. And if this firewall wants to be clever and say, what, I'll just compute all possible combinations, this is exponential. In just this one sequence here, we've got 4 different sequence numbers and 8 different possible values for that byte. So we have 16 possible combinations, and the attacker can keep doing this, cause the firewall to take up an exponential amount of space, and suddenly this becomes a DOS vector as well. So this is actually pretty difficult for the stateful packet filter to defend against. And the key is the stateful packet filter has no idea which packets are going to reach the destination and which don't. So the firewall is, getting confused because all these packets are being sent. It has no idea which ones will reach the end. So it has a hard time reconstructing this connection. So now our original rule of don't allow the word root through has been broken. We can break it relatively easily. All right, questions on how this attack works, because it's a little bit finicky, but I think it's really cool. All right, we're almost to the end. There are some other kinds of firewall. So maybe instead of letting packets through or not through, we're actually going to be a little bit more invasive, I guess would be the right word. A proxy firewall, instead of allowing packets through directly, is actually going to form 2 TCP connections. So the client tries to connect to the server. The firewall blocks this and say, no, actually, you're forming a TCP connection with me. And then the firewall makes its own TCP connection with the server. So now instead of 1 TCP connection, we actually have 2. This firewall is really a man-in-the-middle attacker. So it can really easily spoof the addresses of the 2 end hosts. So to the client and to the server, it just looks like, oh, I'm just sending TCP data. So it looks normal to them. But this firewall now has access to the direct TCP byte streams because they're the ones in charge of the sequence numbers and whatnot. So they don't have the problems with packets. They are the ones reconstructing this connection. And if the client tries to do anything finicky with the times to live, they'll just give a garbled result to the firewall, and the firewall will send the garbled result back to the server. So the firewall in this case is actually proxying this TCP connection instead of just inspecting the packets that go in it. You can actually go even higher with this. So instead of TCP, you can actually proxy at the layer of the application itself. Now, the application has to support this, but this is actually supported in quite a few protocols. So in HTTP, for example, there are HTTP proxies, and these actually parse the entire HTTP request, read it, reconstruct the request, maybe with a couple of additional headers for the proxy, and send that to the server. The server sends its response. The proxy parses the response, sees, oh, this is what the response is, great, and then sends that back to the client. So now instead of just TCP connections, we're going even higher and we're proxying at the level of HTTP. So you can keep going up and up and up with these firewalls. And as you go up, you sort of trade off the fact that the firewall can now parse this data more effectively at the expense of now this firewall is more complicated and it might be slower as well. So we've got pros and cons with these, but there are other types of firewalls and not just packet filters. So some alternatives to allowing firewall traffic, you don't only have the only option available to you isn't just punching a hole in your firewall. You could do something called a virtual private network. Now, I know everyone's heard of the term VPN. It's kind of a buzzword nowadays in marketing, but a VPN is really just some set of protocols that allows you access to an internal network via some external connection. So technically what it does is it creates an encrypted tunnel, and internal network traffic is sent through this encrypted tunnel that's sent through the internet. So the intuition here is kind of like you are emulating a software Ethernet cable and you're plugging in your computer directly into the network, but it's not actually an Ethernet cable. It's just a tunnel that you're forming to some VPN server. So it's kind of clever. The firewall in this case is going to allow all VPN traffic. And this kind of has the drawback of now any arbitrary traffic can go through this VPN tunnel, but it's kind of one of the trade-offs that you make. So now instead of just opening up your server to the entire internet, you can create a VPN server that your computer can connect to. And now you have access to the internal network and you can securely access your network resources instead of just punching a hole in your firewall. So there are alternatives. Just wanted to let you know that these are available. And we can talk about how VPNs are used in the privacy space after lecture. I know that tends to be a hot marketing topic in recent times anyway. All right, so some pros and cons of firewalls. Some pros, they allow for centralized management of security policies. So there's a single point of control that everyone can use. You don't have to deal with individual devices, just entire networks are covered by your one firewall. It's transparent to end users. So usually your users are just using the internet and it doesn't even look like, an angry pop-up appeared on their computer because you're just managing the network. And finally, this does mitigate security vulnerabilities on the end hosts. For example, you could set up a firewall rule that blocks anything that looks like shellcode. So you mitigate the memory safety vulnerability because you're blocking the attacker's access to the input to the server that would allow them to exploit it. Of course, with pros come cons. In a firewall, you're reducing the network connectivity. So depending on your threat model, this could be a bit annoying because now you can't connect to as many things as you used to be able to. Some applications simply don't work well inside a firewall. They're like, hello, I need full access to the internet. I just cannot function like this. You also have that vulnerability to insiders. So I mentioned all the way at the beginning that the typical threat model for firewalls is based on trusted insiders and untrusted outsiders. But if you consider that employees could be bribed or threatened, and devices are often brought from the network or from the outside world into your network, this could be more dangerous than you would imagine because the outside is secure, but on the inside, it's still, soft and vulnerable. The result of this is that once you have one compromised device, your entire network can quickly be compromised by attackers. So there are pros and cons to this. You can mitigate this by layering internal firewalls. So maybe you have an outer layer that is somewhat protected and an inner layer that's like super protected. You're not allowed to bring any devices in, but this is still one of the cons. All right, to summarize, we talked about denial of service, which is the attack on availability. Availability is making sure users can access the service, and we deny this in several ways. At the application level, we can attack the algorithms that applications are using or simply just exhaust their resources. And some defense here is to identify traffic, isolate users from each other, and impose quotas. Or you could also talk about proof of work, which just requires users to spend resources. And now the attacker has to spend resources to cause you to spend resources, and it becomes harder for them. On the network level, we're typically just flooding the network bandwidth or the packet processing capacity. We can do this in a distributed manner, so attacking using multiple computers, or in an amplified manner, which uses an amplification server to turn a small input into a large output that is sent to the victim. You can even combine these two, and we see really large attacks that come with distributed and amplified DOS. And we can defend against this using packet filtering. All of these DOS attacks can also be defended against using over provisioning, where you just purchase a lot of things so that the attacker has to overwhelm more resources. For SYN cookies, we talked about SYN flooding, where the attacker sends a bunch of SYN packets that cause the server to allocate a lot of state for these TCP connections. And we mitigated this by creating SYN cookies. So instead of storing the state on the server gives the state to the client. Then the client says, here is my state. Like, now that I finished the connection, you can store it. And then the server will verify it, store it, and only then does it consume memory. Finally, firewalls. We can defend many devices just by defending the network. And by defending the network, to defend the network, we need a firewall. This firewall is controlled by security policies dictating how traffic on the internet is allowed to be sent or not sent. And this can be implemented with packet filters, which can be either stateless or stateful, or they can be implemented using proxy firewalls. And attackers have ways of subverting packet filters, usually by splitting payloads or exploiting the time to live, although there are, of course, other attacks. So we are 1 minute over, but that is the end of this lecture. So thanks for coming out. I'll stick around for a couple questions if anyone has any. I have a raised hand. Feel free to unmute yourself and ask it.
Yeah, so I had a question about firewalls.
Okay, I don't know if other people hear this, but your audio seems a bit noisy. You feel free to ask it in chat as well. I'll keep the recording going until you ask it. But everyone else, you're free to leave unless you have your own questions.
Yeah, is it any better now? Okay, cool. So I'm from like a different country where like the internet, actually some websites are filtered.
Oh,
So
yes, censorship.
If that's just a massive firewall on the entire country that like restricts you from going to a certain website.
Yes, so censorship is a topic that's sometimes talked about in this course. We might talk about it as a special topic if we have the time. But in censorship, yeah, either it could be just a giant firewall. So if you've heard of China, the country is relatively well known for something called the Great Firewall of China. So those will work either by completely dropping packets. If it's a man-in-the-middle attacker, it has the ability to do that. Sometimes it's not a man-in-the-middle attacker. So, the country's network is really large. Maybe it can't man-in-the-middle all of it. But what it can do is it can also be an on-path attacker. And if it sees a connection to a website that it doesn't like, it will execute a reset injection attack. So if you remember, a reset injection is where you can see the sequence numbers and then you send a reset packet to make it look like that connection was immediately aborted. So those are generally how sensors block traffic to websites that they don't like. Does that kind of answer your question?
Yeah, so like a follow-up question to that is, like, in the same country, you can use VPN to go wherever you want, right? And I know the government's crazy enough to like block that way, like block it if it was possible for them to block it. So is there no way to just like actually keep your firewall even if they're using VPN?
Yeah, so the key, I guess I didn't have a diagram for VPNs, but maybe it would be a good idea to have in the slides in the future. But let's say that we've got some, can you see me drawing on my screen? It's
Yeah.
Not very beautiful, but it's okay. Let's say we have, I don't know, let's say Google is censored. So this is Google, and this is you. I don't know why I'm drawing stick figures. This is totally unnecessary. If I try to make a connection directly to Google, this firewall is going to notice it and block that connection. So it'll execute a reset injection, or it'll just drop the packets if it's a man in the middle. But what a VPN allows you to do is, let's say there's a VPN server in, I don't know, Norway, just as an example. What you can do is, if your firewall doesn't block VPN traffic, then you can form an encrypted tunnel. And oh no, that's not what I wanted to. Okay, I'll redraw this. And now what you've done is you've basically punched a hole through the firewall, because you can send data through this tunnel that the firewall can't see. So you send the data, route it through the VPN server, and then you connect to Google. So you're sort of bypassing the firewall, because all it looks like to the firewall is a VPN connection to this server here. And assuming that that's not blocked, there's nothing that the firewall can do, because the firewall relies on being able to see traffic and being able to block traffic, but it can't do that with a VPN. Of course, if your VPN server was located inside the firewall, then you haven't really made much of a, then it wouldn't really work. But does that answer your question?
Yeah, thank you.
All right. If there are no other questions, I will go ahead and stop the recording. See you, everyone.